Reaction enthalpies can be determined using calorimetry only for reactions that go to completion, are fast, or have no side reactions. For reactions that do not meet these criteria, the reaction enthalpy can be determined indirectly using Hess's law. Hess's law states that when a reaction can be expressed as the algebraic sum of two or more reactions, then the delta H for the reaction is the algebraic sum of the delta H of the reactions added. Basically, the reactants and products in individual steps can be added like algebraic quantities in determining the overall equation and enthalpy change for that reaction. Let's show you this by using a simple example. Typically, using Hess's law, you'll be given a couple of equations that you as givens. And then what you're going to do is manipulate these equations to solve for the equation in question. In this particular example, we want to determine the enthalpy change for the reaction below. I have 2D gives me B plus 2E. I want to know what is the delta H of that reaction. So we're going to use these two equations and manipulate them, either flipping them, which if I flip them, I change the sign on my delta H, or multiply by some factor and then multiply delta H by that factor. Add the two equations and sum them to equal this. If I do that, then I can add up my delta H's, and that tells me the delta H for this reaction. So to do this, typically we look for a species in the desired equation that occurs only in one of the given equations and manipulate the equation to place the species on the correct side in the correct number of moles. So I'm going to look for D, B, or E in these equations and try to find it in one of the equations why it's by itself. Let's start. Usually I start from left to right. Let's look at D. Can I find D in one of the two given equations by itself? The answer is yes. If I didn't, then I would move on to the next one. I want something that I can figure out what I have to do to that particular equation. So I only want one species in that equation, not species that's in both equations. For example, A. A is in both equations, so I don't want to mess with that. I want to mess with things that are by itself. So, if we examine the desired equation, we will notice that D occurs only in equation 1. We then have to ask ourselves a couple of questions on how to manipulate equation 1. First question is the species on the correct side of the equation? Well, in our equation of question, we want D on the reactant side. Is D on the reactant side on the given equation? The answer is yes. So that means we're going to use this equation just like it's written. We're not going to flip it and change the sign. The second question is, does it have the correct number of moles? In our equation, we want to end up with 2 moles of D. Do I have 2 moles of D in this equation? The answer is no, I have 1. So what we're going to do is multiply this equation by 2. 2A, 2D, 2E, 2C, which means I have to do what to delta H? Multiply that by 2 as well, because it's an extensive property. So it would be 2x. So what I end up is, this first given, I manipulated it. It is 2A plus 2D gives me 2E plus 2C's, and my delta H now is 2x. Now I'm going to do the same thing to the second equation, but I'm going to have to look for it and see what species is available that I can manipulate it to see what I got to do to get this equation to work. Well, looking at it, we see that I have B only in that second equation, so I'm going to do the same thing. I'm going to ask it, is it on the correct side in this equation? Well, I want it on the product side. Where is it in my given? It's on the reactant side, so it's not in the correct place. So that means I'm going to flip the reaction, change it to 2C goes to 2A plus B, which means I've got to change the sign on my Y to a negative. The second question is it the correct number of moles? Well, I need 1 mole, and it is 1 mole, so I'm not going to multiply it by any factor. I will use it just like it is after I flip it. So that gets me 2C, gives me 2A plus B. Delta H now is a negative Y. Now, I've done something to each of the givens, so now I will take those givens and add them up and see if it gives me the equation in question. If it does, then I've done it correctly, and all I have to do is add my delta H's. If it doesn't, then I have a problem. I need to look at it in a little more detail and see if I made a mistake somewhere. So, we then add the two equations to determine if we attain the desired equation. To obtain the delta H for the desired equation, we add the manipulated delta H's. If we do this, we obtain the following. We took the first one, remember, and we multiplied everything by 2, including delta H. The second one, we took that and flipped it and changed the sign. Let's add the two equations. If I do that, you see that I have 2c on both sides, which cancels out. I have 2a on both sides, which cancels out. So then I bring down everything that's left, and I have 2d gives me b plus e. The question is this the same as the equation in question? And the answer is yes. I needed 2d giving me b and 2e. That means all I have to do now is add the delta h's that I manipulated, and that'll give me my delta h. So in this case would be 2x minus y kilojoules. Notice you can easily check your manipulation of given equations. If you did everything correctly, the overall equation will be exactly the same as the desired equation, which in this case, it is in an example. Now, let's do this now with some real chemistry. Here's my givens. I have sulfur plus oxygen gives me sulfur dioxide, and I have a delta H of a negative 297. I had sulfur trioxide giving me sulfur dioxide and oxygen with a 198 kilojoules. We're going to use this data to obtain the enthalpy change for the following reaction. So our goal is this reaction right here. I want 2 sulfurs. I want 2 sulfurs plus 3 oxygens gives me 2 SO3s, and I want to know what the delta H of that. So I want to look at these two equations, equation 1 and equation 2, and I want to see if I can find the species. So I'm going to go left to right and look for that species and see if it's in one of those equations by itself. If it's not, then I move on. Good example, oxygen. Oxygen's in both, so I'm not going to worry about that one. I'll just continue on. So, looking at what we got, do I have a species in either one that I can look at and manipulate an equation? The answer is yes. Sulfur solid. We can see that's only in the first equation. So we look at that, and next question we will ask ourselves 2 questions. One, is it on the correct side? And after that, how many moles do I have? Okay, so the first question, is sulfur solid on the correct side? Yes, I need it on the reactant side, and it's on the reactant side, so I'm not going to flip it. I'll use the equation just like it is. Second one, is it the correct number of moles? Do we have the correct number of moles? The answer is no. I have 1 mole of sulfur solid, and I need 2 moles. Okay, I need 2 moles in my final equation. So I'm going to end up multiplying everything by 2. So now we did something to equation number 1. Now we got to see if we can find something in equation number 2. And the thing that we're looking at is SO3. I see that SO3 is only in the second equation. So I will take that and ask my questions. First question, is it on the correct side? It's on the product side for my question, and it's on the reactant side for my given. So therefore I got to flip the reaction. And then when I flip the reaction, I got to change the sign on my delta H, which means put a negative in front of it, making it, instead of the endothermic, make it the exothermic reaction. Second question, is it the correct number of moles? Well, I want to end up with 2 moles of SO3, and I have 2 moles of SO3, so no, I don't have to multiply it by any factor. So what we have to do is take the first equation and multiply everything by 2, take the second equation and flip it. So if we multiply the first equation by 2 and reverse the second equation, hopefully they will sum up together and give me the reaction in question. So the first one, I multiplied sulfur solid by 2, the oxygen by 2, the SO2 by 2, and my delta H by 2. I've taken the second equation and flipped it. Now I got 2 SO2s. I have O2 on the reactant side and 2 SO3s on my product side. Since I did that, I changed the sign on my delta H and multiplied it by -1. Now I will add my 2 equations, And when I do that, I see that my two SO2s cancel out, bring down the rest, 2 sulfurs. I have 2 oxygens and 1 oxygen. That's a total of 3 oxygens. And I bring down my 2 SO3s. So the question is this the reaction in question? And the answer is yes. This is exactly what I'm looking for. So that means all I have to do now is add my delta H's. I'll take my 2 times a negative 297 and add it to a negative 198, which gives me a total delta H of a negative 792 kilojoules. So this is equivalent to 792 kilojoules of heat being released. Notice that the overall equation is exactly the same as that it was desired. Therefore, the sum of the delta H is equal to delta H of this particular reaction by using Hess's law. Homework 55. Notice in the homework you may have to use fractions as multipliers to figure out things to get them to cancel out, like 4/3 or etc.